Today actually we are going to start the new lecture on structural analysis of nanomaterials. This is the broad name of our course, that is structural analysis of nanomaterials. This is very much essential for the scientists, researchers, students, or maybe the persons those who are actually dealing the materials in their research or maybe day to day life or maybe making any kind of products. So, generally these subjects is a very essential subjects from which we can get the informations about the materials, how they behave, and based on their crystal structure, their atomic bonding, and also the preparations of the different types of materials, and then after that how the new crystal structure is forming, or maybe how they are behaving, or maybe whatever the new materials has been formed over there. So, and it will also give you the inside picture of that particular materials, that how they can behave, or maybe they can show their physical properties, or maybe the chemical properties, or maybe the structural properties. So, basically actually this chapter is divided into so many sub parts. So, first we will discuss about the crystal structure, atomic bonding, then we are going to discuss about the different types of materials like the metals, ceramics, polymers, some kind of advanced materials preparations, and then later we are going to discuss that about the XRD, generally by which we can get the informations about the crystal structure of that particular materials, and the last also we are going to give some kind of new techniques like the XPS or maybe some kind of other methods by which we can get the crystal structure for that particular material. So, simple, in a single word I can say that this subject will give a wide informations about the crystal structure and their properties for a particular material. So, today actually we are going to start our first lecture, which is nothing the introduction lecture. So, fundamental concepts of atomic structure and their interatomic bonding. So, first before going to start, let us know that why it is required to study the atomic structure and the interatomic bonding. So, generally in the structure of materials, generally what is the relationships when we are getting the properties of materials. So, first is the structure of materials and the properties of materials, and in between the relationship. So, relationship will give you the particular essence that how the material will behave, or maybe what kind of material I can add. So, what will be the new crystal structure formations, means it is a some kind of, in a single word you can say that that is a some kind of X-ray kind of view of that particular material. From that we can get the informations about the physical properties of that particular materials, or maybe about the chemical properties of that particular materials. So, some properties in solids strongly depends on the type of atomic structure and the interatomic bonding. This is well known fact. This we have gone to our in class 10 standards or maybe class 12 standards. So, of course, every material is having some atomic structure and the interatomic bonding, because the atoms are closely packed with some bonding, otherwise the atom can go randomly anywhere. So, there should be some force which can act in between the atoms. So, atomic level structure can strongly influence the material performance. So, this is the vital point over there. So, what are the material performance? Generally we can talk about the modulus, we can talk about the melting point, we can talk about the coefficient of the expansion. So, it directly defines the properties of materials. Yes, of course, from that particular point of view we can get the informations about the materials like carbon as diamond and the graphite. Here right hand side you can see some kind of things, that graphite and diamond we have given the example. So, graphite it looks like dull, opaque, soft, and the common materials, means easily available. When we are talking about the diamond, it is very brilliant and transparent, and it is having some glittering or maybe some kind of reflective in nature. It is very hard, and it is also the rare earth materials because it is not easily available. You can prepare it some kind of artificial diamond, but with some help of high end equipment. So, generally you can see the crystal structure of the graphite, and you can see the crystal structure of the diamond also. So, crystal structure of the graphite is the layer by layer stacking, and in the diamond it is a closed pact of the carbon atoms. So, first let us know what is the atomic structure. So, generally atoms is equal to nucleus. Nucleus is constituted by two things, that is the protons and the neutrons, and another one is called the electrons. So, atom is divided into two groups, one is nucleus, another one is electrons. So, here in this atom, so it is the nucleus of that material. So, it is divided into two parts, neutron and proton, which is nothing but the nucleus, and another one is coming from electron. So, charges, electrons are negatively charged particles, protons are positively charged particles, and neutrons are electrically neutron. So, this is the three characteristics of these three. So, what is the magnitude of electrons and protons? Generally 1.6 into 10 to the power minus 19 coulombs. What is the masses? Generally protons and neutrons masses are 1.67 into 10 to the power minus 27 kg. For electron it is 9.11 into 10 to the power minus 31 kg. What is the atomic mass unit or maybe the AMU? So, generally it is 1.66 into 10 to the power minus 27 kg and equals to 1/12 mass of the carbon atom. So, what is the atomic number? Generally it is generally denoted by number of protons, which is equal to number of the electrons. What is the atomic mass? So, generally it is proton mass and the neutron mass. So, a mole is the amount of matter that has mass in grams equal to atomic mass in AMU of atoms. So, the number of atoms in a mole is called the Avogadro number. He is a famous scientist who discovered these numbers, and so the Avogadro number is 6.023 into 10 to the power 23 atoms. So, first let us know the behavior of electron. So, generally it is a wave like behavior. So, dots in this particular case represents the individual electrons and lines represents the pairs of electrons in a covalent bond. So, in this case you can see some dots over there, so which is represents the individual electrons. So, electrons have a wave like behavior such that we can only give the probability of an electron being in a particular volume. More accurate representation of an electron is as a cloud. Quantum mechanics is used to describe the wave behavior of electron. Generally electronic structure of an isolated atoms, characteristics of the electrons wave like nature. Electrons are in orbitals, each orbital is at a discrete energy level determined by its quantum number. So, generally electrons are present and then there is a gap. So, the electrons are present in like a orbital, it is like our galaxy. So, what is quantum? So, generally for n principal energy level, generally we are giving the designations like K, L, M, N, O, like 1, 2, 3 etc. For I subsidiary orbitals, generally it is S, P, D, F, generally 0, 1, 2, 3 up to the n minus 1, and for Mi magnetic it is 1, 3, 5, 7, it is from minus I to plus I, and Ms spin generally it is half or maybe the minus half. So, these all are the different types of electronic structure. So, now we are going to discuss about the electron energy states of isolated atoms. So, electron have very discrete energy states, tends to occupy lowest available energy state unless excited by the external source of energy. So, we have to give the energy to the electron so that the electron can jump from the lower level to the higher level itself. So, this is the energy level. So, 1s it is the K shell where n is equal to 1, and when we are increasing the energy it is going to the up to the 4p or maybe the 4d, which is nth cell, that is n is equal to 4. So, what is the stable electronic configurations? The electron configuration is stable only for the noble gases. Except for noble gases, the outer shell is not completely filled because there is some vacancy. So, one or more electrons may be lost or gained to form an ion or shared in a covalent bond. Have complete S and P subcells, tend to be very unreactive. So, here you can see the element and atomic number and the electronic configurations. So, for hydrogen generally it is 1s1, for helium it is 1s2 because atomic number is 2. So, when we are talking about the say suppose carbon, so it is 6, that means 1s2, 2s2 and 2p2. So, it is total 6. When you are talking about the magnesiums, it is 12, 1s2, 2s2, 2p6 and the 3s2. When we are talking about the argon, it is having 18 like 1s2, 2s2, 2p6, 3s2, 3p6. So, it is so on. Now, we are going to discuss about the periodic table. So, elements are arranged with increasing atomic number. Elements in group or column have similar valence electrons and the physiochemical properties. So, elements in group 8A. So, if we are talking about the 8, so 8 group or maybe that 8A group, in this particular case it is inert gas. So, stable electron configurations helium, neon, argon, krypton, xenon, radon and the Og. So, in group 7A, so we are talking about the 7A. So, here is the halogens, 1 or 2 electrons deficient are there. So, like for fluorine, chlorine, bromine, iodine like that. In group 1A and 2A, so when we are talking about 1A and 2A, alkali and the alkaline earth metals, 1 or 2 electrons in excess like hydrogen, lithium, sodium, potassium, like beryllium, magnesium, calcium like that. In group 3B and 2B, so generally here is the 3B and here is the 2B. So, in this particular case these all are the transition metals like strontium, like zinc, like cadmium, like mercury, so on. In group 3A, 4A and 5A, so in this particular case the 3A, 4A and 5A. So, this group, so it is the intermediates between metals and non-metals like boron, carbon, nitrogen or maybe aluminum, silicon, phosphorus, gallium, germanium, arsenic, so on. So, what is the electronegativity? Tendency of an atom to accept electrons, that is why it became the negative. So, electropositive elements readily give up electrons to become the positive ions. So, it is losing the electrons. Electronegative elements readily acquire the electrons to become the negative ions. So, it is accepting the electrons. It increases in moving from left to right and top to bottom. So, it increases in the moving from left to right and from the top to bottom. Now, what is the atomic bonding in solids? So, atoms are bound to each other by number of bonds, as we already know. So, atomic bonding focus on what made the atoms to cluster together and how atoms are arranged. Yes, as I told already, we are having so many atoms. So, there should be some bonding, no? Then only the atoms can come close together and give a compact shapes over there. So, what is the principle of the atomic bonding? It is considered as the interactions between two isolated atoms as they are brought into close proximity from an infinite separations. So, bonding force and about their energies. So, when two neutral atoms are brought close to each other, they experience attractive or maybe the repulsive force, as we know. So, it is like a magnet. So, attractive force due to electrostatic attractions between electrons of one atom and nucleus of other. What is repulsive force? Due to the repulsion between electrons and the nuclei of the atoms itself. So, net force acting on atom is sum of the attractive and the repulsive force, of course, which is given by F net is equal to F attraction and the F repulsion. So, when Fa and Fr become equal, there is no net force, that is Fa plus Fr is equal to 0. So, as state of equilibrium, center of two atoms will remain separated by equilibrium spacing rho. So, two atoms will counteract any attempt to separate them by an attractive force or to push them together by a repulsive action. So, potential energy between two atoms is given by E is equal to integration F dr. So, for atomic systems generally En is equal to integration infinity to r Fn dr, which is nothing but the integration infinity to r Fa dr plus integration infinity to r Fr dr, because for the attraction and for the repulsion force, that means En is equal to Ea plus Er. So, here En, Ea and Er are net attractive and the repulsive energies for two isolated and the adjacent atoms. So, in this particular case you can see that atomic force is in this particular case and then the repulsive force, and then we are getting the net force here in this particular line. So, this is known as the RO. So, if we put a tangent over there. So, in this particular case also, so this is generally for the dependence of the result repulsive, attractive and net force on interatomic separations for two isolated atoms. Here the dependence of repulsive, attractive and net potential energies on interatomic separations for two isolated atoms. So, now we are going to discuss about the bonding energies and melting temperature for various substances. So, generally bonding type we are going to know that ionic for like sodium chloride or maybe the magnesium oxide. Then what is the electron volt per atom or ion or maybe the molecule, what is the bonding energy? It is 3.3. What is the melting temperature? It is 801. When we are talking about the covalent bond, generally silicon or maybe the carbon, so its bonding energy is 4.7 and melting temperature is 1410. For carbon it is 7.4 and it is more than 3550. When we are talking about the metallic, so for the generally the metals, metallic bonding, so metallic bonding like aluminum it is 3.4, its melting temperature is more than 660 degrees centigrade. When we are talking about the van der Waals bonding or maybe the van der Waals interactions, so generally for argon it is 0.08 and the melting temperature is minus 189, it is very weak bonding. When we are talking about the hydrogen bonding, generally for the ammonia we are getting it 0.36 and the melting temperature is minus 78. So, now we are going to briefly discuss about the atomic bonds. So, generally the atomic bonds has been divided into two parts, one is called the primary bonds, another one is called the secondary bonds. So, primary bonds is divided into three parts, that is ionic bond, covalent bond and the metallic bond, and secondary bonds is two types, one is called the van der Waals bonds or maybe the interactions, another one is called the hydrogen bonds. So, what is interatomic bonds? So, primary bonds generally ionic, covalent and metallic bonds are relatively very strong and grouped as primary bonds. So, metals and ceramics are entirely held together by the primary bonds itself. Ionic and covalent bonds are present in ceramics while metallic and covalent bonds in metals. So, when we are talking about the secondary bond, generally van der Waals and hydrogen bonds are relatively weak, termed as the secondary bonds, as I told already. They provide links between the polymer molecules in polyethylene and other polymers which make them solid. So, now first we will discuss about the ionic bonds. So, it exists between two atoms when one atom is negative and another is positive. Ionic bonds are the strongest bond found in metallic and maybe the non-metallic elements, non-directional in nature. So, like the best example is that salt, sodium chloride. So, sodium chloride, in this molecule there are more electrons around chlorine forming Cl minus and fewer electrons around sodium forming the Na plus. So, Na plus and Cl minus, positive and negative. So, in this particular case when the sodium is reacting with the chlorine, so excess electron is jumping onto the chlorine atom and sodium became the Na plus and the chlorine became the Cl minus. So, it is like that. So, Na plus and the minus, some electrostatic attraction is taking place in between that. What is the properties? It is very hard, brittle in nature, electrically and thermally insulative, high melting and the boiling point. Now, we are going to discuss about the covalent bond. It exists when electrons are shared between the atoms to saturate the valency. Covalent bond formed between non-metal or maybe the non-metal or maybe the metalloid and non-metal. They are stereospecific and directional in nature, found in organics and ceramics, may be very strong as in diamond which is very hard. Example is the methane CH4. So, in this particular case you can see that C is present in this main orbital and then H is surrounded by this, and these all are attached with the covalent bonds. So, three types of covalent bonds. First one is called the single covalent bond, formed when two atoms bond and share a single pair of electrons. Next, double covalent bond, formed when two electrons pair are shared between two atoms. Each atom contribute to 2 electrons to the bond. And the third one is that triple covalent bond, formed when 3 electrons pairs are shared between two atoms. Now we are going to discuss about the metallic bond. Metallic bonds are the forces of attractions between free floating valence electrons and positively charged cations. Strength of metallic bond: higher the charge, the greater the metallic strength, found in metals and their alloys. Example of metal elements like sodium, lithium, magnesium. So, what are the properties? Like high melting and boiling points, good conductor of heat and electricity, hard, dense and have tensile strength, malleable and ductile, and it is very lustrous, means glittering in nature. So, here are the bondings in the metals. So, due to that ions, so generally the bonding are taking place, and that should be the charged cations. So, now we are going to discuss about the types of secondary bonds. First, it is the van der Waals force. It is a very weak, already I told you, the weak intermolecular forces of attractions between the individual molecules have bonding energies of 10 kilojoule per mole, it is equivalent to 0.1 electron volt per atom. These forces arise from atomic or molecular dipoles found in inert gas and molecules that are covalently bonded. So, there are three types of generally van der Waals forces. First one is called the dipole force, exist only between polar covalent molecules. Second is dipole induced dipole interaction, exist between one polar and one non-polar covalent molecules. And the last one is called the London dispersion forces, exist between two non-polar covalent molecules. So, this is the London dispersions example. So, in this particular case you can see that two non-polar covalent molecules, and in between that it is the dipole induced interactions example, and it is the dipole interaction. Next, we are going to discuss about the hydrogen bond. It is a chemical bond between hydrogen atom and an electronegative atom. Generally we can find it like HF, HN, HO bond, generally it is called the hydrogen bond. Electronegative atoms are fluorine, nitrogen, oxygen. Intermolecular hydrogen bonding is stronger than the van der Waals force. So, properties of the hydrogen bond. So, hydrogen bonds are directional. So, have low melting and boiling point, no valence electrons, hence good insulators. So, soluble in both polar and the non-polar solvents, they are transparent to the light. Example, best example is the water and the some ammonic molecules. So, now we are going to discuss about the effects of bonding on the properties of materials, how it affects. Two important factors contributing to properties of materials is the nature of bonding and of course the atomic structure. So, first we are going to discuss the covalent bond. So, bond energy is 5 electron volt, melting point is high, hardness in terms of ductility it is hard, and ductility is very poor, electrical conductivity usually low, and the examples diamond, graphite, germanium, silicon. It is ionic, generally the bond energy is 1 to 3, melting point is high, its hardness is hard, ductility is very poor, electrical conductivity is low like sodium chloride, zinc sulphide and the CaCl. So, when you are talking about the metallic, it is 0.5 electron volt, its melting point varies, hardness also varies, and electrical conductivity is very high like iron, copper, silver, etc. Van der Waals force, it varies from 0.001 to 0.1, melting point is low, then hardness is soft, but ductility is also very poor, electrical conductivity is also low like neon, argon, krypton, like that. And last one is the hydrogen, its melting point is very low, hardness is soft, and ductility is poor, usually low, and generally the example is the ice or maybe the water. Now we are going to discuss about the crystal structure. So solid materials are classified according to the regularity with which atoms or ions are enhanced with one another. Two types of solid materials generally, one is called the crystalline materials, another one is called the non-crystalline materials. So what is the crystalline materials? Atoms are situated in a repeating or periodic array over large atomic distances. Long range order exists which provides a repetitive 3D pattern. Formed by all metals, many ceramic materials and some polymers. Its properties depend on the crystal structure of materials like density, ductility, etc. Examples: crystalline silicon dioxide, generally known as quartz, sodium chloride. So you can see the crystalline silicon dioxide crystal structure. Then we are going to discuss about the non-crystalline materials. So it is having very lax systematic and regular arrangement of atoms over relatively large atomic distances, possesses complex atomic or molecular structures, also called the amorphous or maybe the supercooled liquids. Rapidly cooling through freezing temperature favors formation of a non-crystalline solids. What is the example? Amorphous silicon, glasses, plastics, rubber, etc. Now we are going to discuss one very interesting thing, that is called the unit cell. So it is the smallest repetitive volume which contains the complete lattice pattern of a crystal. So it is the one, you can say, one small backbone kind of things. So crystal lattice depicts three dimensional arrangements of constituent particles like atoms, molecules and the ions of crystalline solids as point. Lattice parameter. Lattice constant is the physical dimension of unit cell in a crystal lattice. This part I will briefly discuss in the subsequent lecture. Lattice in 3 dimensions have 3 lattice parameters like A, B and C. Alpha, beta and gamma are the angle between the axis. So if you see the lattice parameters, so here this angle is alpha, then this is beta and this is the gamma one. So lattice point, this is the unit cells. So this is denoting by A, this is B and this is C. If it is the cubic one, then A is equal to B is equal to C. So generally unit cell is characterized by type of atom and their radii R, cell dimensions A and C for the hexagonal structures, number of atoms per unit cell, that is N, coordination number, that closest neighbor to atoms, and atomic packing factor, that is APF. These all in brief I am going to discuss into the second lecture. So what is crystal systems? Based on length, equality or inequality and their orientations, the angles between them, alpha, beta and gamma, a total of 7 crystal systems are defined. 7 crystal systems are cubic, tetragonal, hexagonal, orthorhombic, rhombohedral, triclinic to monoclinic. Total 14 Bravais lattice fall into 7 crystal systems. So this is the example of the rhombohedral systems, monoclinic and the triclinic, then tetragonal, then cubic like BCC, body centered cubic, FCC, face centered cubic. This is the orthorhombic systems. So total these all are the different types of Bravais lattices. So now we are going to discuss about the different crystal systems with axial length and the angle. So for generally cubic, as I told already, it is A is equal to B is equal to C, because all the length are same because it is cubic. Angle, it is perfectly 90 degree to each other. So alpha is equal to beta is equal to gamma is equal to 90 degree. Bravais lattice, it is simple, generally sometimes it is body centered, sometimes it is face centered also. When we are talking about the tetragonal, it is A is equal to B, not is equal to C. Alpha, beta, gamma is equal to 90 degree, generally it is simple and the body centered one. Orthorhombic, A not equal to B, not equal to C, is equal to alpha is equal to beta and gamma, all are 90 degree. It is simple, body centered and the face centered. When we are talking about the rhombohedral, A is equal to B is equal to C, alpha, beta and gamma are not 90 degree, it is simple. It is hexagonal, A is equal to B, but not is equal to C. Alpha beta is 90 degree, but gamma is 120 degree. It is simple, hexagonal, close backed. Then monoclinic, A not equal to B, not equal to C. Alpha is equal to gamma is equal to 90 degree, but not the beta. It is simple. Next one is the triclinic. It is A not equal to B, not equal to C, alpha not equal to beta, not equal to gamma, not equal to 90 degree. It is very simple. So now we are going to discuss about the crystal planes, that is Miller indices. A system of notations is required to identify the particular directions or planes to characterize the arrangement of atoms in a unit cell. Now it is the very interesting one, that is called the Miller indices. So they are the notations to describe the planes and the directions in a crystal. Planes are directed by H, K, L are given by the reciprocal of the intercepts of plane on the 3 axes. So 1 by H, 1 by K and 1 by L. So the plane which intersects x axis at 1 lattice parameter and is parallel to y and z axis has Miller indices like H is equal to 1 by 1 is equal to 1, K 1 by infinity is equal to 0 and L 1 by infinity is equal to 0. So it will be written as HKL value 1 0 0. So in this particular case, so you are having x is equal to 1. So this is your starting point. So from this you will come, so you will come 1 unit over here and then your K and L value is almost 0. So y and 0. So you are talking about this plane itself. So that is the 1 0 0 plane. Then you are coming to 1 and then your L is also 1 is going, but this is 0. So you are talking about this plane itself, that is 1 1 0 plane, and 1 1 1 is this plane only. So this is known as the 1 1 plane. So like this way we can calculate the total plane of that particular crystal structure. So Miller indices directions. Vector of convenient length is placed parallel to the required directions. The length of vector projection on each of 3 axes are measured in terms of the unit cell dimensions. These 3 numbers are made to smallest integer value known as indices by multiplying or dividing by a common factor. The 3 indices are enclosed in square brackets like this way. In the third brackets U, V, W. A family of directions is represented by in this manner. So less than U, V, W, greater than. Now we are going to discuss about the Miller indices plane. So determine intercepts of the plane along the crystallographic axis in terms of unit cell dimensions. If plane is passing through the origin, there is need to construct a plane parallel to the original plane. So take the reciprocals of these intersect numbers. So first you are making a plane, so it is passed through the origin itself. So now take the reciprocal of these intercept numbers, clear fractions reduced to set of smallest integers. The 3 indices are enclosed in parentheses like within first bracket HKL. A family of plane is represented by second bracket, that is HKL. Miller indices useful conventions. If a plane is parallel to an axis, its intercept is at affinity and its Miller indices will be 0. Never alter the negative numbers. This implies symmetry that crystal may not have, or maybe use bar over the number to represent the negative numbers. If it is -1, so generally we are giving it as a 1 bar. So a plane or directions of family is not necessarily parallel to other planes or directions in the same family. The smaller the Miller index, more nearly parallel to the plane to that axis and the vice versa. Multiplying or dividing a Miller index by constant has no effect on the orientations of the plane itself. When the integers used in the Miller indices contains more than 1 digit, the indices must be separated by commas like 3, 10, 13. Now some useful conventions for the cubic crystals. So UVW within the third bracket is normal to HKL. Is U is equal to H, V is equal to K and W is equal to L. Example 1 1 1 perpendicular to 111. So, here UVW is parallel to HKL if HU plus KB plus LW is equal to 0. Two planes H1 K1 L1 and H2 K2 L2 are normal, like H1 H2 K1 K2 plus L1 L2 is equal to 0. Two directions U1 V1 W1 and U2 V2 W2 are normal if U1 U2 plus V1 V2 plus W1 W2 will be 0. Interplanar distance between family of planes HKL is given by DHKL is equal to A by root over A square plus K square plus L square. So, this is the known formula. Angle between two planes is given by cos theta is equal to H1 H2 plus K1 K2 plus L1 L2 by root over H1 square plus K1 square plus L1 square into root over H2 square plus K2 square plus L2 square. So, now we have come to the last of this particular lecture. So, it is the time to summary or maybe the summarize the whole lecture. Here mainly we have discussed about the forces between the atoms, different types of forces we have, like some hydrogen, then van der Waals forces and some kind of forces we have used. The forces may be both attractive or maybe the repulsive in nature. The net force is important to decide the bonding strength in between the atoms. Here three types of chemical bonds, generally ionic bonds, covalent bonds and metallic bonds we have discussed elaborately, and each bond is having their own applicability. Based on that, the material crystal structure or maybe the material physical properties or chemical properties is totally dependent. Thank you.